So here is part D of the 2007 Form B free response question number 6. And in part D, they define this new function h of x. And h is dependent on f. It's f of x minus x. Explain why there must be a value r in between 2 and 5 such that h of r equals 0. Now, if you watch the video that had the solutions in it for parts A and B, we used the mean value theorem, and we used the mean value theorem because it said something about a derivative being equal to a certain value. And in this case, it says, must the function equal a certain value? And if you think back to some of the things that we've looked at this year that have guaranteed that a function has to equal a certain number, the one theorem that we can kind of point to that had to do with a situation like that was the intermediate value theorem. And so the intermediate value theorem is here. And the intermediate value theorem says if you have a function that's continuous, so it didn't depend on derivatives at all, as long as your function is continuous between a and b, and w is any number between f of a and f of b. So w is a y value that's in between these two locations on the y-axis. Then there is some number c in between these two x values for which that function evaluated at that x is going to equal y. So, reading it doesn't really make a lot of sense unless you're really careful, but if you think about it graphically, it really does make a lot of sense. If we have a function that's continuous from a to b, like this graph definitely is, and we pick any y value, they call this y value w, that's in between these two y values, we're guaranteed that there's going to be some x in between these two, they're calling that xc, that's going to have the capability of producing the function value of that intermediate y value that we've chosen. So no matter where you pick, if w is here, 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 look at your graph. You're going to have a point on the graph that is produced by some x value in between a and b. You have a point on the graph here that's produced at some x value in between a and b. You have a point on the graph here that's produced by the function value at some x value in between a and b. So in part D of this question, it might be useful to us to use that theorem. So what we probably are going to want to do is we're going to want to compute the y value of h at 2 and at 5. So I want to compute h of 2, and h of 2 is going to be equal to f of 2 minus 2, right? I'm just putting 2 in place of this x and in place of this x. And they tell us what f of 2 is. They tell us that f of 2 is equal to 5. So I can put 5 in place of f of 2, and h of 2 ends up being 3. If we computed h of 5 as well, h of 5 ends up being equal to f of 5 minus 5, just putting 5 in place of the x's in h, and f of 5 we know the value of. That we've used already once or twice. F of 5 is 2, so I'm going to be looking at 2 in place of this, and then minus 5, giving me a value of negative 3. So basically what this tells us about the graph of h, if I attempt to sketch it here, and sorry that that's not really horizontal, but it'll do. If this is a graph of h of x, if we go 1, 2, 3, 4, 5, 1, 2, 3, and 1, 2, 3, we basically now know that 2, 3 is on the graph of h, right? That's from this top calculation, and 5, negative 3 is on the graph of h. So as long as we can verify that h is continuous as we go from this point to this point, we're going to be able to use the intermediate value theorem to say that h has to be equal to 0 at some x value in between 2 and 5. So let's see, is h continuous? Well, f of x is twice differentiable, and since it's twice differentiable, it's differentiable, and if it's differentiable, it's got to be continuous. This individual component of h is continuous, x is always continuous, so the difference of two pieces that are continuous is still going to be continuous. So h of x is continuous based on what we just said, and if you were explicitly trying to write this proof, you'd want to write that out. I'm not going to, since it takes me a little bit longer to write with this, but h is continuous, and so by the intermediate value theorem, since h of 2 is 3 and h of 5 is negative 3, and 0 would be in between those two y's on the y-axis, we're guaranteed that as we go from this point to this point, no matter what the graph looks like, whether it's linear, wavy, what have you, you have to cross the y value of 0 to get from here to here with a continuous graph. The intermediate value theorem proves that for us.